Hello, this is Eric from UNC Charlotte. Mutexes is only the simplest mechanism to synchronize multiple threads. We will see today that there are other mechanisms that can be used to provide synchronization in parallel applications. There are different variants of locks that are useful in different scenarios. The operating system kernel usually provides mutexes. They are kernel objects that enforce correctness by leveraging the operating system. If a thread tries to lock a mutex that is not available, the kernel will unschedule the thread and not schedule it again unless the mutex becomes available. Because they are managed by the kernel, different processes can share a kernel mutex. Spin locks are a user space shared memory implementation of locks. They are essentially complicated loops, polling a Boolean variable. Using spin locks means that when a thread cannot acquire a lock, the thread will keep trying to acquire the lock. Mutexes make it cheap to wait for a lock to become available, but the locking and unlocking operations are kernel space operations. It makes mutexes somewhat expensive even if the locks are available. Spin locks are incredibly cheap to lock and unlock, as long as it is not necessary to wait. If waiting is necessary, the thread will burn CPU resources by actively waiting on the resource to become free. This can consume lots of electricity and can even bring the system to a halt if there are more threads waiting for a lock than cores available in the system. A mutex is a best of both worlds approach. It essentially couples the user space and the kernel space approach. If the lock cannot be acquired in user space reasonably quickly, the kernel will provide the locking guarantee. This makes most good cases be as cheap as a spin lock. But if there is an extended wait, the thread will eventually fall asleep. In most threading libraries, what is referred to as a mutex is actually a mutex. FIFO locks ensure that the threads are awakened in the order in which they attempted to take the lock. They are mostly useful to enable a fair distribution of the resource to the different threads. The only one thread can hold a lock model is good in a context where many threads try to update a variable or a data structure. But there are plenty of cases where a data structure is mostly read and almost never written. Think for instance of an ETL system that gets new data once a day. The rest of the day, all access to the data is purely read-only. We don't need exclusive access to the data unless there is a need to update the data itself. This is the situation that read-write locks were designed to solve. They provide two separate locking primitives, a shared lock and an exclusive lock. The semantic is that multiple threads can hold a shared lock at the same time, but if a thread holds the exclusive lock, no other thread can hold either locks. In C++, this feature is provided by stud shared mutex. The lock and unlock function of the object are the exclusive access primitives. The lock shared and unlock shared functions enable multiple threads to hold the lock. Mutexes only provide a way for threads to wait for a resource to no longer be used by another thread. But it does not provide a feature for a thread to wait for an arbitrary event to happen. Maybe a thread needs to wait until some results become available. For instance, it is common in a producer-consumer system to have a consumer wait for a work queue to have some work in it. Condition variables are a synchronization primitive that enable this type of usage. In C++, condition variables are implemented using the stud condition variable any object. All languages implement them in a similar way. Condition variables are paired with a mutex. In order to wait on the condition variable, the mutex needs to be locked. The wait operation will take a predicate, a test that indicates whether the event the thread is waiting on has happened or not. Note that the mutex protects the predicate, so the predicate will only be evaluated when the lock is held by the thread. As long as the event has not happened, the lock will be released and the thread will sleep. Once the event has happened, the thread will awake and reacquire the lock. Two other functions can be used to notify one or all threads waiting that the condition has happened. Consider the following code that simulates two threads playing ping-pong. Two Boolean variables indicate whether one of the threads has scored and which thread should be playing next. The synchronization between the two threads will be provided by a mutex and a condition variable. A thread acquires the mutex and loops until one of the two threads has scored. Then the thread will wait for its turn to play. It is typical for the predicate in the call to wait to be implemented using a lambda function. Note that the two threads wait on opposite predicates. Once a thread is awake, it will check whether the other thread scored, and if not, it will play by displaying a message and by flipping the ping bit. With low probability, it will score, and in all cases, it will awake the other thread. Note that awakening the other thread is not instantaneous, because the lock is still held by the thread that just played. Therefore, the other thread cannot resume until either the first thread exits the loop and calls unlock, or calls wait on the condition variable which releases the lock as long as the thread is asleep. We have seen in this video that there are needs for synchronization between threads that goes beyond the capabilities of a simple mutex. Read-write locks provide a mechanism to optimize the access to data structures that are mostly read-only. Condition variables enable a thread to wait for an arbitrary event to occur.